All right, hello, welcome to today's webinar. It's on portable exchange plant softening operations, the technology. My name is Daniel LeBlanc and I work for WQA's Education Department, and our speaker today is Charles F. Chubb-Michaud, who's with Systematics Company. So anyone who hasn't been on one of these webinars before, there's a little box, it's called the control panel, and the orange arrow will help move the screen out of the way. That way, if you want to get a clear view of what is being presented. If you do have a question or a problem during the webinar, there is a raise hand button. You click the orange arrow to bring the box out, and then you can click that button, and it lets us know that you do have a question, and then you can type the question into the little box that is in the lower portion of that control panel. So this webinar is the first in a series. There will be one on best practices in ensuring customer safety. That'll be followed by one on resin, and then a fourth one on meeting customer expectations and selecting a third-party laboratory. That's going to be a two-part webinar. And then we will close the series with one on plant operations. So today's presenter is Charles F. Chubb-Michaud. He is the CEO of Systematics. He has 40 years experience in the industry, and he has been with or contributed to participated with activities with WQA for the last 30 years. He has got the Award of Merit for Technical Contributions, and in 2014 he received the award for WQA Hall of Fame. So I will turn this over to Charles. Just let me get a second to get the screen over to you.
Welcome, everybody. We're going to be discussing portable exchange plant softening operations today. My name is Chubb. I'll be your presenter. To start, by way of introduction, as brine discharge regulations become more restrictive, portable exchange softening, or PES, is gaining popularity both out of necessity and as the practical solution to meet these restrictions. So this particular presentation is part one of 3 parts, and as Daniel mentioned, resin functionality and plant operations will be scheduled in later presentations. Purpose of this presentation is simply that the management, the operators, and the technicians associated with the production of the portable exchange regeneration plant often come from different directions with different levels of training and different understandings of how things work. So we put this series together to avoid areas of conflict and put everybody on the same page. So we're trying to provide a basic understanding of the information that's out there so that everybody speaks the same language. This course will introduce, this total course will introduce a standard of best practices arrived at collectively by a panel of professionals intended to set a baseline for the successful function and understanding of plant design and the associated technologies while keeping conservation in mind, green practices, water conservation, brine recycle, etc. So this is part one, the technology. To look at an overview, we'll look at ion exchange softening, the process itself, a little bit of the history, how resins are made, the things that drive resin operation being equilibrium and kinetics. We'll discuss the functionality of resin, selectivity, how you can decide what the best application is for the best choice of resin for the best applications. And we're going to do a little bit of chemistry just so that we have a common vocabulary in talking about ion exchange. As I point out here, the water chemistry is simple chemistry, but it is indeed chemistry. So with that, introduction to Chemistry 101. The best reference that you can actually have is the good old familiar periodic table of the elements. This table was developed in the mid-1800s by a Russian chemist, Mendeleev. What he did was took the known elements at the time and arranged them in a series of families that exhibited similar properties. And this table is pretty much refined to reflect his original design. And by family, we're talking about under the 1, 2, 3 designations in Roman numerals. The modern charts are 1 through 18 in Arabic numeral. But you'll see in that column 2A, beryllium, magnesium, calcium, strontium, barium, radium. These are the elements that we know that contribute to hardness, and they're all in the same family. You look at another family over to the right, fluorine, chlorine, bromine, iodine. These are the halogens. They all do a lot of the same things. They have very similar properties. And to the far right, the inert gases, helium, neon, argon, krypton, xenon, all have similar properties. So this, by knowing how one particular element behaves, we can kind of predict in that family how others will behave. So this helps in the selectivity of what we do to remove it. Over to the far right, there's a jagged blue line that runs down through the chart. That separates the nonmetals from the metals, and the nonmetals combine with oxygen to form acids such as boric acid, carbonic acid, nitric acid, phosphoric, sulfuric. You'll notice that arsenic is in that group of nonmetals. Arsenic forms arsenates. It's an anion. It's not removed by softening. Cation resins will deal with this large purple area. These are all metals. Metals tend to form bases in water, things like sodium hydroxide, potassium hydroxide, calcium bicarbonate. These are all alkaline bases. And this is the part of the periodic table that we can address with portable exchange softening. To help with the definition, the periodic table lists elements. The elements, all matter contains elements. These are the building blocks of the entire universe. Elements are made up of electrons having a negative charge, protons having a positive charge, and neutrons having a neutral charge. And I'm showing over here on the left, this is helium. Helium has an atomic number of 2, and that 2 is the number of protons contained in its nucleus. And you'll find that all of the elements will have a number. If you look at the periodic table, all the numbers are filled in, so there's no mysterious element hiding in between boron and carbon. They're in sequential order. We see an AW equal 4. That's the atomic weight. The element that we have here is helium, atomic weight 4. That 4 is arrived at by combining the number of protons with the neutrons. That is a total of 4. Looking to the right, we have carbon, element number 6, and you'll see 6 little pluses in the nucleus. That's the number of protons. The atomic weight is 12. That's the combination of the protons and the neutrons. And if we look in the orbits, we'll see the electrons, negatively charged electrons. Element number 6 has 6 electrons. the number of electrons and the number of protons is always balanced to make a neutral charge. So all elements are neutral. If we look at the yellow band over here, that represents the outer orbit. The white band represents the inner orbit of the electrons. There are a total of 6. Electron orbits like to be satisfied with either 0 or 2 or 8 electrons in the outer orbit. So for helium, we see that it's perfectly satisfied with 2 electrons in the outer orbit. For carbon, we see that there are 4. And that orbit likes to be satisfied with a certain number, and that's what gives rise to valence, which is the number of charges that the ion would have when it's fully neutralized by having 8 in the outer orbit. So let's look a little. That's a lot to digest if you're not into chemistry. So here's a simple compound called sodium bicarbonate. Here's the sodium. Sodium as an element has 1 electron. Remember, it was over in that far left column. Has 1 electron in the outer orbit. Oxygen has 6. Carbon, as we just discussed, has 4. Another oxygen, and hydrogen having 1. The atomic number of hydrogen is 1. It has 1 proton, no neutrons, and 1 electron. Now, in order for these compounds to form, they have to group in such a way that we can have that magic number in the outer orbit, 0, 2, or 8. So if we look at this, we can see that when this is dissolved in water, a lot of electrons are going to move around. I show this in the next slide, but we can come back to this one. And by way of definition, a salt is the product of neutralization of an acid and a base. It's not just sodium chloride, it's potassium bicarbonate, it's calcium nitrate, it's a combination of an acid and a base. And the telltale designator for an acid is a compound with hydrogen showing in it, and the definition of a base is a compound with hydroxide showing in it. So why are the inert gases inert? Well, helium has 2 electrons in the outer orbit, neon 8, argon 8, krypton 8, and so on 8. All of these have perfectly satisfied outer orbits, so they're non-reactive. Inert gases have nothing to give up, and they require nothing in return, so they are indeed inert. If we look at elements combined as a compound, to the left I'm showing sodium chloride, and sodium chloride is neutral because both of the elements are neutral. You can see that the sodium has that 1 electron in the outer orbit, and chloride, being way over in group 7, has 7 electrons in the outer orbit. When we dissolve this in water, we form a sodium ion and a chloride ion. And when this salt splits apart, it doesn't split apart into its element, it splits into ions. So what happens with the sodium? By definition, the positive ion is a cation and the negative is an anion. So what happens when this splits? The chloride will gain an electron, making it negative. The nucleus remains unchanged. So here's the one little lone electron in the sodium ion, and that's going to move over to the chloride ion. So now the sodium ion has 1 less negative charge, which makes it positive. And if you look at this outer ring, now the new outer ring has 8 electrons. And chloride that had 7 has gained 1, so it's perfectly satisfied with 8. But because it gained a negative electron, it has a negative charge. Now, all water contains salts. Salts such as those of calcium and magnesium we know cause scale formation in heaters and boilers. That leads to more frequent maintenance, shutdowns for cleaning, and we call that group hardness. Other salts, such as arsenic, nitrates, fluorides, have MCLs, maximum contamination levels, that the EPA has mandated are not to be exceeded in order for water to become safe to drink. So the portable exchange that we're going to discuss will address both cations and anions, and their functional resins that remove those. So ion exchange is the exchange of ions in solution for less objectionable ions. In the salt-regenerated world, we do not reduce total dissolved solids. We are simply exchanging a calcium for a sodium or an arsenic for a chloride. We're truly exchanging a less desirable ion for a more desirable ion to fit a particular need. So we take out nitrates from well water in exchange for chloride to make it potable, or we remove hardness from feed water to prevent scaling. How does it work? In the center, I'm showing a cation exchange bead in the sodium form. So the resin, and we'll explain how and where this happens, the resin is loaded with sodium. As calcium and magnesium enter the bed, they pass through the resin. And because of this dual charge, see, both of the cation magnesium have dual plus charges, the selectivity is higher than that of sodium with single charge. So for every calcium that pops on, 2 sodiums pop off. This doesn't really increase the total dissolved solids of the water, other than the very, very slight effect of calcium having an equivalent weight of 20 and sodium having 23. So the water would go from 20 parts per million, say, as calcium carbonate to 23. But otherwise, the same number of ions, the same number of reactive ions are in solution. And looking a little at the history of ion exchange, this was first observed in the mid-1800s. Agronomists working with fertilizer and soil and the uptake of such and how it worked found that when they made a mixture containing ammonia and poured it through soil and collected the water on the other side, that it had changed in composition, that the ammonia was removed and calcium and magnesium and sodium showed up in the water. That investigation showed that zeolites, natural clays in soil, had the ability to store fertilizer, in this case ammonia, and release other ions in its place. A German pioneer by the name of Robert Gans developed synthetic zeolites that were regenerable, and this could be used to soften water. He made a big hit in the laundry industry and other industries where the hardness, the scale caused by hardness, was interfering with the process. This was all done over 100 years ago. So the softening industry became a reality at the turn of the 20th century, the very early 1900s. So more on history. It had been known prior to, from the mid-1800s, that salts in solution could interchange ions to form new salts by passing through what we now know is an ion exchange media, be it natural zeolite or synthetic. The reaction is simple. Here I'm showing calcium chloride and sodium carbonate passing just together will interact and form calcium carbonate, which precipitates out, and sodium chloride. Now that is of some value in like lime softening or soda ash softening, in that you can precipitate the hardness and have a soft water solution pass through. It was postulated that if one end of that salt could be made immobile or insoluble, the other end could act as the exchanger, but you would retain the media in some kind of a vessel, and this would avoid having to do the filtration. In other words, if this calcium carbonate was tied down in some way, then the soft water would simply pass through. So here we're showing a similar reaction, in this case hard water, calcium bicarbonate. The big O here represents a resin bead in the sodium form, very much like what I'm showing up here as sodium carbonate. This is sodium resin. And when water passes through it, the divalent +2 charge calcium jumps on the resin, the sodium pops off. And that is softening. It was further discovered that by passing a concentrated solution of brine, sodium brine, through the resin, that you could force the hardness back off. In other words, a reversible reaction with a regenerable product. So here's the resin. It's loaded with hardness. We pass sodium chloride brine through it. We put sodium back on the resin. We end up with calcium chloride in the effluent and a little bit of excess sodium chloride for the driving force. Modern ion exchange chemistry has not changed any of that. The ion exchange chemistry today simply uses a different substrate, a different backbone. Rather than zeolite, it's based on a plastic resin. So these are synthesized from styrene. This chemistry was developed in the 1940s. It is basically unchanged for the last 73 years. So water softening. Is it possible to soften water without actually removing the hardness? Yes, it is. There are chemical additives. If you read the labels on a box of laundry detergent, you'll see that there are chelating agents such as citric acid or EDTA that are added to a variety of cleaners to react with and tie up calcium and magnesium ions. So in effect, we're not removing the hardness, we are simply deactivating the hardness. So a proper definition for water softening is the removal of or the reduction in activity of the hardness ions in solution to an equivalent of less than 1 grain per gallon as calcium carbonate. That's a little bit of a concept. That's calcium carbonate, parts per million as calcium carbonate. It's a little bit hard to grasp that you can have water containing parts per million as calcium carbonate even though the water does not contain calcium carbonate. Soft water, for instance, at 0 hardness is measured in parts per million as calcium carbonate, referring to the sodium and the chloride. There is no calcium, there is no carbonate present. We won't get into that part right now, but it is part of the chemistry. What the conversion does is it converts the milligram per liter of the element into ions, the number of ions. And the number of ions always has to be equal. The milligrams do not. So why do we soften water? Well, if we look at this from a little bit of a back door, we see that hard water will precipitate when you heat it. In other words, calcium bicarbonate, which is soluble, undergoes a chemical change when you heat it, and it drives off part of the CO2 and forms water with the excess oxygen, and you end up with calcium carbonate. Calcium carbonate is an insoluble scale. So hard water will form scale when it's heated. It will form precipitate when you increase the pH, because you either convert the bicarbonate to the carbonate salt, or you convert the calcium to the hydroxide, which is lime, and this is also insoluble. Calcium bicarbonate does not exist as a solid. If you have water containing calcium bicarbonate, typical tap water, when it dries down on a dish, on your car, on your windows, on your clothes, when it dries down to a solid, it converts to calcium carbonate. So scale forms even from water that has soluble calcium in it as it dries. It precipitates when you concentrate it, such as on the surface of an RO membrane. So simply by allowing hard water to evaporate slightly and increase in concentration, it can precipitate and form scale. It forms a reaction with soap. The soap molecule is soluble. It's a sodium salt, usually lauryl sulfate or some other long chain oil-soluble anion portion. When that reacts with hardness, it forms a calcium lauryl sulfate, which is a soft, scummy precipitate. I'm sure you're familiar with bathtub ring. This sticky, dull residue forms when soap is added to hard water. It's incompatible. Hard water is incompatible with many chemical formula, and it forms a precipitate. Now that's what hard water is. What is soft water? Well, soft water does none of the above, and that's why we soften water. It's more than just prevention of, it's more than just the prevention of scale in your water heater. It's all of these. Soft water actually in a residential application versus hard water will save the housewife or the house dad, whoever cleans, about 40 hours a year of extra cleaning by not having to repeat what they just did to polish it up. So if you have to wipe spots off your silverware and your dishes and fluff up your clothes and towels to keep them from being scratchy, soft water saves you time, and that's the big plus of water softening. So going a little further, what are these resins and how are they actually produced? On the left, I'm showing the chemical formula, if you will, for vinyl benzene. I'm sure you've heard divinyl benzene. Well, this is the vinyl benzene. Vinyl is this double bond carbon group at the top. You see this double bond. And benzene is this six-membered ring, C6H6. That is a benzene ring. In the modern vernacular, we write it this way, and I'm sure you've seen that chemical symbol somewhere in the past. That is benzene, and we leave out all the hydrogens, and we simply represent the vinyl group as such. Well, when we form divinyl benzene, it's really a vinyl benzene with an added reactive group. So how does this all go together and form an ion exchange resin? The process is known as polymerization. Here I'm representing our monomer, a single molecule of styrene, and I'm going to break that double bond at the top, extend it out the other way, and I'm going to put it side by side with a little catalyst and some heat, and I'm going to form a chain reaction that produces a polymer of incredible molecular weight. It will, if you've ever used polyester casting resin, where you pour a liquid on a piece of wood and it hardens into a glassy solid clear plastic, that's polymerization. We do the same thing here. Now I'm putting the divinyl benzene into the linkage because that acts as the cross-linker to connect to other strands of polystyrene. Those in turn have their own divinyl benzene. So a resin bead that you look at is essentially one big molecule with several million molecular weight, totally intertwined and interconnected in this fashion. That's why they are so insoluble, so hard, and chemically inert. So how do we make these beads? How do we get these little buggers to come out round? There is a process called suspension polymerization developed in the 40s, unchanged today, but this gives you a random size distribution. You can duplicate what's going on here by looking at one of your bottles of oil and vinegar dressing. The oil floats, that's the monomer. The water sinks, that's the dispersant. You shake them and you form a whole series of small droplets, and those are the pre-polymer beads. If those beads are catalyzed and heated slightly, then they turn solid. They cross-link into a solid little bead. Jetting is a more modern technique of forming beads. This is like a small blunt hypodermic syringe that's being pulsed. It puts out tiny little droplets into a flowing stream of water. These droplets are very uniform in size, and they form very uniform beads. Not all resins are made by jetting. Not all resins are made by suspension polymerization. There's also a technique called seeding, where a copolymer is formed as a very tiny, tiny particle under a high shear dispersion, and then these polymers are used as the base or the seed for growing larger. So it's a little bit like growing crystals by dropping a crystal into, if you've ever worked with the crystal gardens where you have a silicate solution, you drop a crystal in and it forms what looks like coral because the seed will grow larger. So we have a copolymer now, which is actually a water white, crystal clear, tiny, tiny little bead. And that's represented on the left as the polystyrene. How do we make this into an ion exchange resin? Well, we do that through a process called sulfonation. By treating this with a concentrated sulfuric acid and a little heat, we can actually break into the chain and add the sulfonate group to the benzene ring. And that reaction is shown down below, where we have the CH of the benzene ring reacting with H2SO4, which is sulfuric acid. We're splitting out water, and this SO3H group attaches directly to the ring of the plastic, the polystyrene. Now that hydrogen remains mobile. It's the hydrogen ion part of acid, and that can be converted to any cation going. If we replace that H group with sodium or potassium or lithium or ammonia, we make an ion exchange resin in these various forms. Softening would use sodium or potassium. But going back to the earlier premise that if we can make a salt with an immobile partner by wrapping it into a small ion exchange bead and only have a portion of that bead take part in a reaction, we form an ion exchange substrate or a resin. So the resin itself is insoluble, but the hydrogen is reactive or the sodium is reactive. So by putting this in a tank and screening the tank so we don't lose the resin. You pass water through it, we get the chemical reaction, we get the softening reaction, and the bed remains in place. So what do these resins actually look like? I'm sure if you've seen them, they look like glassy little spheres. And that's called a gel resin. And a gel resin is indeed a glassy little sphere. But when we sulfonate it, we actually make the resin strand water-soluble. It's the cross-linking that ties the strands together so that it doesn't become soluble. So it's like putting a rubber band around dry spaghetti. Put a half a dozen rubber bands over the length of all the little noodles, throw it in water, cook it, it stays together as one big chunk without disappearing. That's essentially what the clear gel resins are. They have a surface area of about 3,800 millimeters square. There's about 600 square millimeters in a square inch. So you get an idea that a gram of gel resin would have a surface area of about 6 square inches. They appear solid. They're actually about 50% water. They are moderately cross-linked, usually in the range of 6 to 10%. Most of it is 8%. And the way they react depends primarily on diffusion. This is called a gel, so it's a lot like Jell-O. You take a little packet of powder, you add water, you cool it down, it looks like a solid, but it's really mostly water. There's also a resin that's referred to as a macroporous. These appear opaque, and they are quite a bit different. They consist of a whole series of open channels and solid. The surface area is upwards of 1,000 square meters per gram. Compare that to the millimeters, 6 square inches versus a football field. There is a continuous solid and void phase. So if you picture a plastic bucket, you fill it with ice cubes, you pour in molten paraffin or melted wax, and the wax goes through all the holes around all the ice cubes, and then it sets up. And the latent heat from the wax melts all the ice and the water runs out. Well, since all the ice cubes touched each other and all of the holes were continuous, we now have a porous network resembling a macroporous bead that has both a continuous solid phase and a continuous void phase. These can be made much higher cross-linked and much more resistant to heat and chemicals, but the kinetics is based on the huge surface area. There's very little penetration of water, very little diffusion, but we have such a tremendous surface area. Now, what do these things actually look like? By comparison, the surface area per gram, 6 inches versus over 10,000 square feet. What do they look like? This is a blown up photo of a macroporous bead. You can see that there is a continuous phase or a solid phase that is three-dimensional. It goes all the way through, and at the same time, if a tiny, tiny little speck of an ion were to enter the bead, it could pass all the way through it because there is a continuous void phase. Interesting. So what are the advantages of macro versus gel? The macro is generally higher cross-link, therefore it has a higher chemical resistance. It has a higher thermal deformation, or more heat resistance. It has lower moisture because it is higher cross-link. So the higher the cross-linking, the lower the water content because the strands of that spaghetti are more tightly bound. So kinetically it's a little slower, but you make up for that with the extremely high void space. Water is able to pass more quickly through the bead and therefore get to the reactive sites. but because it has void space, there's less plastic, and the plastic contains the functionality, therefore a little lower capacity. Depends on surface reaction. That makes it easier to clean. This is like a gloss paint versus a flat paint, or a ceramic versus an unglazed tile. Because the surface is so hard and impermeable, you can get iron off it a little easier. You can get organic fouling removed more easily because you can use harsher treatment to clean it. It's a more expensive process, uses a few more steps, and for that reason in softening, portable exchange softening, it's a little less popular. But there are applications involving high chlorine and or severe conditions that make it very practical. It'll outlast a gel resin by a factor of 10. So looking at the properties of resin, how does the manufacturer know that the resin he made is correct? Well, you can't simply build a column and run hard water through it and say, yep, this is a good one. So the resin manufacturers have a series of tests, they're quality control tests, that tell them that the resin is put together properly. The first one is moisture. The moisture content of a gel resin, for instance, is known for each level of cross-linking. So a simple moisture determination, which is a dry down moisture, you take a quantity of the resin, you surface dry it by patting it with a paper towel or running dry air through it, and then you weigh it, and then you put it in an oven, and you evaporate all of the moisture, and you weigh it again. And the difference between the wet weight and the dry weight gives you the percent moisture. We do a capacity test on the resin. This is not a hardness capacity per se, but we totally regenerate the resin, say, with acid, and put it 100% in the hydrogen form. And then we run caustic through it, which is sodium hydroxide, and we put an excess caustic through it, which gives us the removal of some of that sodium, and we titrate what comes out the other end, and by difference, we know how much sodium was picked up. We know the weight of the resin, we know the moisture, we know the dry solid content, and we can then calculate the number of sodium ions per gram of resin that was removed. This is capacity. It's total capacity. Typically for an 8%, that total capacity is in the range of 43,000 grains per cubic foot. A bead count, this isn't counting 1, 2, 3, it's a count of the whole perfect bead, the crack beads, and the pieces. If the resin is 50% fractured beads, something went wrong. Typically it would be above 90 and often in the range of 99 whole perfect bead. The mesh size, mesh can be controlled, but we'll measure mesh size to show that the extremes on the fringe edge of the bead distribution are within range, typically 1 to 2% that are on the large side and 1 to 2% that could be on the small side. I'll get into a little more of this later. When resins change form, say from hydrogen to sodium, they shrink. When they go from sodium to calcium, they shrink more. When you regenerate the resin back to hydrogen, it swells. So we can go through a cycle, measure the volume of resin, and we can measure the swelling ratio. What this tells us is whether that cross-linking is uniformly placed. If all the cross-linking is side by side, then the remainder of the bead swells incredibly large amount. It could triple in size. By having the mortar in the bricks, so to speak, evenly spaced, we have a very uniform and measurable swelling. So this is a QC test that tells us if our physical mixture was properly done prior to. With an anion resin, we measure both strong base and weak base functionality. That's part of a later discussion, but it's very important because as a resin degrades with age, the strong base functionality, which is the ability to remove nitrates and fluorides and so on, degrades to a weak base functionality, which is the ability to remove acid. Very different if you're splitting sodium arsenate and taking the arsenic out versus arsenic acid or hydrochloric acid as a strong acid. Weak base is not used in the portable exchange salt regeneration because it doesn't respond to salt. So we're very careful about what percent of weak base functionality creeps in. And weak base is caused by degradation of the strong base. So if you made the resin correctly, the weak base functionality is a very minor part of the total makeup. So we measure that ratio, and we also measure that down the road to show the degradation as it proceeds, because resins do degrade with time. Color is not a specification. Resin is what resin is, and once you lock in the process, the resin may be light amber in color, it may be a medium or dark, and you can even force it to go completely black. But resin is not a specification. Not all plants can make all colors. So we spoke of cross-linking. So what is the cross-linking all about? Well, this is the mortar that holds the brick wall together. If all the mortar is in the foundation and you simply stack the bricks, that's not a very strong wall. So the idea is to get that cross-linking evenly dispersed throughout the entire polymer bead. If we make up resins with known cross-linking, we can measure the moisture. Obviously, a low cross-link resin has more swelling and therefore a higher moisture. If the moisture is higher, there's less plastic and we have a lower capacity. So by going up the scale in cross-linking from a 2, 4, 6, etc., we see the moisture comes down and the capacity goes up. Typically, we work with an 8% cross-link. Runs 46 to 48% moisture, 1.9 to 2.0 milliequivalents per ml. Now, a milliequivalent per ml is the same as an equivalent per liter. So when we measure the capacity of resin, we report it as MEQ per ml, milliequivalents per milliliter. This is a chemical function. A milliequivalent is 1/1000th of an equivalent, or expressed as the milligrams of sodium or calcium or whatnot that you can actually exchange per milliliter, 1/1000th of a liter of resin. So it's a quantitative measure of capacity per unit volume. To put it in other terms, grains per cubic foot, equivalents per liter, milliequivalents per milliliter. You could even do it in pounds per cubic meter or square foot or cubic foot, cubic yard, anything you want. It's an expression of a chemical equivalent per unit of volume. And we typically work in the 8%. If you go to a 10% for better chemical resistance, moisture comes down. That means the kinetics drop a little bit. The capacity goes up because you have less water. It's a little more of it's a narrower street, a little more difficult to drive that big truck down the street if it's narrow. If you get into the extremes of cross-linking because of chemical need, in other words, you have to boil it in concentrated acid and you want it to hold together, these resins are very low in moisture, kinetically very slow, but they have great capacities. Going back to our Buddy the periodic table, we would expect the selectivity of a resin to increase when we increase the molecular weight, because those resins have a strong, or those elements, ions, would have a stronger charge. So if you have a water softener that's taking magnesium and calcium, and you also have radium in the water, how do you know when you've hit the capacity for the radium? Well, if it's still removing calcium and magnesium, it surely is still removing radium, because it has a higher selectivity and a higher capacity for radium than it does for calcium. On the other side, we look at fluorides, chlorides, bromine, and iodine. The selectivity goes up as the molecular weight goes up. As we move down the periodic table within a family, the selectivity is higher. We can take iodide ion out of water very readily with a strong base anion resin. Remember, on the right-hand side of this squiggle, these are all anions. So iodine is very readily removed. Fluoride, on the other hand, is somewhat difficult to remove with a chloride form resin because it's below chloride in selectivity. It still reacts, but very limited capacity. So we use chloride and we use sodium as our regenerants because it pretty much takes out everything south of it, and as you go across the table and these numbers increase, showing an increase in valence, then the ability to remove also increases. So pulling copper out of water with a sodium form resin is very feasible. Nickel, iron, manganese all come out very readily in a softener. Looking at specific selectivity, and I'll back up to the periodic table and try to memorize the first four here: hydrogen, lithium, sodium, and potassium. And here's hydrogen, sodium, lithium is not present, potassium, and finally we get into hardness and the heaviest lead, Pb+2. And we look at the DVB content, which is the how tightly packed is the solid plastic with the charge. The higher the cross-linking, the lower the moisture, the more reactive media we have built into the bead. So if we equate the hydrogen selectivity to 1 all the way across the board, just as a base, we see that as we go up in molecular weight, and that's down the chart, down the periodic table, and we go across to the other metals, that the selectivity increases. And as we tighten up the bead by making it lower moisture, the selectivity increases. And we go to an extreme in cross-linking, the selectivity increases. So if you were making a filter, say a cartridge filter to remove lead, lead is going to be very highly selective on the ion exchange resin, but the higher cross-linked resins would favor lead removal because the ratio of the selectivity over even that of sodium also increases with increased cross-linking. So picking the right resin to do the right job requires a little bit of this knowledge. So as we go from left to right with higher cross-linking, the selectivity goes up, and as we go down the periodic table, the selectivity goes up. And 8% is your neutral standard softening resin, so it shows that calcium, for instance, is 3 times almost more selective than sodium. That's why the reaction occurs. So just for fun, I'm sure you've wondered, how many beads are there in a liter or a cubic foot of resin? And here are some numbers just to give you an idea of how small the resins are and how big a liter is. There's almost 7 million beads in a liter of resin, over 200 million in a cubic foot. There's an enormous number of reactive sites. Each one of those sites, 3.41 times 10 with 25 zeros after it, can pick up an equivalent of hardness and release an equivalent of sodium. It doesn't tell you that the capacity for removing hardness is infinite. It just says ions are awfully small. We can have up to 56 equivalents in a cubic foot. 56 equivalents of lead is almost 13 pounds of lead that can be picked up on a cubic foot of resin. It's about 2.5 pounds of calcium. Gel resins have a surface area of about 100 square meters per cubic foot. Macros are over 5,000 acres of surface per cubic foot. By comparison, a football field is only about 4,400 square meters, and that could be covered with just 4.5 grams of macroporous resin. In other words, a quarter teaspoon or a half a teaspoon of resin has a surface area of a football field. This is what an ion exchange resin looks like. That's the largest of the beads. That's pretty much the smallest of the beads. And if we look at the actual measurements of a 50 mesh resin, it's about 0.3 millimeters. A 16 mesh bead is about 1.2 millimeters. So the ratio between the largest and smallest is about 4x, four times. And we can get into reactivity, but you don't want that ratio to get too far apart, because the reactivity is inversely related to the diameter. Strictly by diffusion, if it's 4 times as big, it's 16 times slower. When we, fortunately, when we screen a resin and we capture the 16 mesh portion and the 20 mesh portion and the 25 mesh portion, etc., and we weigh them all individually and we plot those weights versus the size on a curve, we get this standard bell-shaped curve. This is called Gaussian distribution. Now, if we want to narrow that, we can do it by screening either side, and we screen out what would appear to be about 17 and maybe 4%. So we screen out about 21% of the resin on either side, and you end up with about 60% of the resin being in a very tight band. If you broaden that a little bit and still make a quasi-uniform bead, say a 20-40 mesh, without the fines and without the marbles, you really have about 92 to 93% of the resin that fits the fairly uniform definition. Now, cation and anion exchange resins, the sodium on the resin, on a cation resin, will, being positive, will exchange for any other positive ion and most heavy metals. Calcium, magnesium, iron, manganese will all be exchanged onto a cation resin. The chloride on the anion, and this is what a strong base anion looks like. Take just a second and back up. Here we have the exchange site on the backbone as an exchangeable positive, and here we have what is called a quaternary functional group, 1, 2, 3, 4, quat, with an exchangeable chloride. So the chloride on the resin will exchange for negative ions, such as nitrate, bicarbonate, sulfate, and most oxyanion metal complexes, such as arsenic, phosphate, chromate, uranium. The resins can be regenerated with any soluble salt to restore capacity into the neutral salt form. Looking at the resin reaction, what's really going on? Well, strong acid cation, as the cation resins are known, will regenerate with either salt or an acid. So they have the ability to split a salt and produce acids. So sodium chloride, which is a neutral salt, if you run that solution through a strong acid cation in the hydrogen form, the hydrogen exchanges for the sodium and you produce hydrochloric acid. So in the sodium form, the resin will remove calcium, magnesium, copper in exchange for sodium, and as a deionizer, demineralizer in the hydrogen form, it removes all of the above plus the sodium, replaces it with hydrogen. Strong base anion can be regenerated with salt or base, and it would produce a base. These are used for nitrate, fluoride, arsenic, alkalinity in the chloride form. So you pull out arsenic, put in a chloride. In the deionizer form, it's the OH form, and it would even remove chloride. So what happens when you run water through a demineralizer? Well, we'll use sodium chloride as an example. The sodium is removed and replaced with hydrogen. Then the chloride is removed and replaced with hydroxide. So the effluent from that system is hydrogen hydroxide, otherwise known as water. Relative affinity for ions and resins. This is a more complete list of the of what's removed and how strongly it's picked up. Here's our sodium form resin. Now we've equated sodium to 1, and you can see that that the resin in the hydrogen form will react very nicely to remove sodium, but in the sodium form, it takes out all of these which are higher. So I had mentioned radon or radium a while back and said if you're still removing calcium, which is almost 2 to 1 over sodium, you're certainly removing radium, which is 13 to 1. Even if the resin is exhausted and in the calcium form, this exchange will still take place. But if you use hardness break as an indicator of the end of the cycle, you will most certainly be removing radium. Not all of these regenerate off that readily. If they're held extremely tightly like lead, it takes a little extra boost in the regeneration to bump those off. You might have to raise the regen salt dose to 20 pounds to get lead back off, as opposed to 6 or 8 to remove calcium and magnesium. On the strong base anions, I've equated everything to the chloride form, and you can see that in the chloride form you can remove nitrite, sulfites, selenium, bromine, nitrate, sulfates, arsenic, all the way up to chromate, which is actually the chrome 6 ion, and it has a very high selectivity over that of chloride. So a strong base anion in the chloride form will definitely remove chromate. And it's hard to explain chromate as chrome 6 because of the ATE, but that's the ion chromate. Oxygen with a -2, there are 8 of them, and that total ion has a -2, so 8 minus 2, that's chrome 6. Chrome 3 is a cation. So any reaction can occur due to mass action. Simply the fact that you have a brand new resin, you can remove fluoride very readily if the resin is new or very clean. And because fluoride has such a low selectivity, it regenerates off almost completely with 3 or 4 pounds of salt. So you can run a chloride form anion to remove fluoride from water should you need to do that. As we go up the chart, selectivity and capacity go up. So what are the driving forces that really shape the ion exchange process? Selectivity is one. The higher the cross-linking, the higher the selectivity, the higher the molecular weight of the element, generally the higher the selectivity. Equilibrium. Equilibrium is driven by the ionic concentration. Higher equilibrium from higher ionic concentration, you get a higher equilibrium with a cleaner resin. A higher, more highly regenerated resin gives you a higher equilibrium. In other words, more complete removal and more of it. Kinetics. Higher cross-linked resins are slightly slower. In 40-degree Fahrenheit water, you wouldn't want to even soften water with a higher cross-linked resin because it's sluggish. A bigger bed is fine, but if you're running 5-6 gallons per cubic foot, it won't completely soften. Higher temperature, on the other hand, gives a higher reaction rate and a better equilibrium. So in a nutshell, what is equilibrium? Well, I'm showing, let's assume that the blue top to this diagram is hard water, and that the amount of hardness is represented by this triangle. And we'll call it 100% hard. Doesn't matter what the grains are. And at this point, let's say the water contains no sodium. It's just calcium chloride. As this goes down through the bed, we reduce the calcium, and we increase the sodium in the water by an equal amount. We're looking at this reaction up here, calcium chloride, sodium form resin. The resin goes to the calcium form and puts out sodium chloride. So further down, we've taken out 40% of the hardness. We put in 40 parts of sodium. And we go all the way down to where we've removed all of the calcium, and now we've replaced it with all sodium. So what do you think is going on as the driving force for the calcium is decreasing and the resistance with the sodium in the water increasing? Well, as the calcium driving force goes down and the sodium driving force goes up, eventually nothing happens. So if you have a very high TDS water and you put a lot of sodium in the water and the resin's starting to get a little exhausted, the reaction won't occur. So nothing happens when you run towards the end of the bed life. And that's what equilibrium is. Not only do you have to force calcium onto the bed, but you have to allow the sodium to come back out. And as that sodium goes up, it becomes a regenerant solution. You can regenerate a bed with seawater because the sodium concentration is 30,000 parts per million compared to the hardness. So you can regenerate it with seawater. So can you turn around and soften seawater? It's difficult. So how can we improve the favorability of this reaction? Well, ion exchange is very fast. It only takes a fraction of a second. It's controlled by diffusion. Smaller resins are faster. It increases with temperature. Warm water is quicker. The completeness of the reaction depends on how clean the bed was, and it favors a neutral pH. So anything between 6 and 9 works very well. And I make a comment here. It's driven by ionic concentration, and it favors the lower concentration, which is a little bit contrary to what I just said about equilibrium. So I'll explain that in as few words as possible. The ion exchange reaction in general favors low concentration, low ionic load, under 1,000 parts per million. If you increase the concentration to an extreme, then you are producing a regenerant during the softening process, and this retards your equilibrium. So the example I gave was seawater. That would be an extreme, 30,000 parts per million. City water, 500 parts per million, works great. How far can you go and still get reasonable performance? The practical limit is to about 4,000 to 5,000 parts per million. You certainly would have no problem at 2,000 part water, even at 30 grains hard. You should be able to soften that in a single pass. If you're at 5,000 parts per million and even 5 grains hard, it's going to be difficult to soften that water in a single pass because, one, the driving force of only 500 parts per million for hardness is low, and number two, the resistance of having several thousand parts per million of sodium is very high. So it's not a favorable reaction, but with a very clean bed, you can do it. So concluding, today's modern styrenic ion exchange resins were developed a long time ago. I like to use the example of 1941 as the precise year because that's the same year I was developed. So we're the same age. Ion exchange resins can react with ions in solution and replace them with ions contained on the resin. As an example, calcium for sodium, that's called softening. The stronger the ionic charge, the higher the selectivity, the more complete the removal. Again, as you move down the periodic table, more complete removal. As you move left to right, more complete removal. The ion exchange process is reversible. It can be regenerated. And water softening protects appliances, saves money by removing scale-forming hardness, saves you time. So that concludes the part one. I thank you all for your participation.
Oh, Chubb?
Yeah.
Hey, I was just checking to see if we could ask if anyone had any questions.
Yeah, no. I just asked, are they all unmuted?
They would have to type them in.
Oh,
gotcha. We wouldn't be able to do the audio. So I've got a screen where if they wanted to type them in. So it's in that control panel. Just click that orange box. It'll open the panel up. And if you did have a question, there's a little raise hand button. If you could just click on that, and then we'd know that you were going to be typing in a question. So in the meantime, while we wait to see if anybody has any questions, I'd like to remind people that there's the next webinar is going to be in 2 weeks, and it's going to be covering the best practices in ensuring customer safety. Okay, the question I have is the numbers given for beads per cubic foot, was that for a gel resin? That
it would be the same. Do you have to type an answer, or are they able to hear me?
No, they can hear. They can hear.
It would be the same for the resin. It really depends on the particle size of the original assumption. I took a 650 micron bead size as being my average bead, so the calculation is really based on that middle of the road size. If it's smaller resin, obviously, being a cube, if the resin was half the size, there would be 8 times that many beads. So a fine mesh, for instance, would have upwards of 30 million beads in a liter.
All right, and I'm sorry, I wasn't listening to the answer, but there's another question that you might have answered when you just answered that one. Is what mesh size does that equate to?
Probably about a 35 mesh. it's middle of the pack.
Okay, and it looks like that is it for the questions. I'd like to thank you again, Chubb, for doing the presentation, and thank everybody
My pleasure.
for participating.
Look forward to seeing everybody back on part 2.